All right, we're live for another episode in a recently put together series with my co-host Jim Green and Jon Radoff, and looking at the future of digital space, frontier technologies, and AI. And today we're joined by a wonderful guest who we're really looking forward to talking to. Matt, welcome to the show. Matt is the CEO of AstroForge, who recently did a mission just here in April and is looking to mine on asteroids and look at space as a potential of having resources. So, with that in mind, welcome to all of you who'll be joining us to watch this series and looking to have a great conversation. So, Jon, Jim, and Matt, let's do this.
Yeah, exciting. We were talking about this a little bit towards the end of our first premiere episode, and it was more about like the overall economics of space. And we got started getting to talking about resource extraction. Jim brought up manufacturing organs in space, but obviously, like if you just sort of take it to the limit, like the economy of space is far, far greater than the economy that the Earth alone can ever be, right? So just there's a lot more space for us to occupy. There's more resources, more everything. We can make things that aren't on the Earth. So this is really exciting because I'm also a science fiction junkie, and we were talking a bit about The Expanse,
Right.
And I met some of the authors who worked on The Expanse actually when I was working on Game of Thrones with George R. R. Martin. He was actually part of this community in Santa Fe where the authors who worked on The Expanse were kind of mentored by him a little bit. But they created this whole solar system idea where the belters are out there on the asteroids and extracting resources, and it was sort of one of the fundamental conflicts. It's a fun story. I don't know that like I believe humans are going to be the ones doing that. Like I don't know, Matt. What do you? I saw you make a look at that. Like, what do you think?
Yeah, there's so many cool ideas about space, and I think, look, at the root of everybody, we all want to dream, and we all love these shows and these movies that come out about space exploration and pushing into the frontier. I mean, look, they've been part of pop culture for years, right? Whether it's Star Trek or Star Wars or whatever show you want to talk about, we've always dreamed about the unknown and what we can do there. The reality is a little more boring, to be completely honest with you. And from the way that we've always looked at this is there's always been these futuristic ideas, and I think they're amazing. Whether we go mine, helium-3, whether we grow or manufacture in space, or whether we mine water. I mean, that was the original concept from a company called Planetary Resources. These are all exceptional ideas, and I think could potentially have a massive market and a massive future that we have to grow into. The reality to me is a little bit different. And keep in mind, as running a company, you really have to look at time indexing and how long that time horizon is before these markets develop. And the reality is, from some of the first kind of concepts of rocket refueling, I mean, those were almost 20 years ago at this point, coming out of United Launch Alliance. They haven't materialized at the rate that I think any of us would have liked to hope, right? And so for us, when we really started thinking about the concept of what we were going after, we did not want to go after an economy that did not exist. That was one of the fundamental rules that we went into this with. Like, if we couldn't find an economy at Earth that had a pretty substantial market cap that we could go disrupt, then there was no point to go take on this mission. At the end of the day, sci-fi is really cool to write about in books, but you sell sci-fi as stories. You don't sell sci-fi as companies. Mm-hmm. And so for us, we've really iterated down to precious metals, specifically platinum group metals. That is what we want to go after and mine. And while I would love to say that we're going to go sell these in space or sell these on the moon or sell these on Mars or whatever, it's actually much more boring than that. We just bring them back to Earth and sell them to actually into the ecosystem that deals with precious metal mining on Earth today. That is really the market we're going after. That's really what we want to disrupt. And I do think that if we want to continue our way of life and build the society that we've started to build, we talk about AI, like platinum group metals are a big part of how we make chips. Mm-hmm. Without them, you're not making chips. In fact, at the STM Foundry in 2020, the reason that was paused for 6 months was actually due to the lack of platinum. Specifically. So going into these things and realizing that our way of life for almost every technology we have kind of relies on these relatively boring, unsexy commodities. That is what we set out to solve. And so I wish I could tell you that we were sending up belters and we were all going to go mine the universe and all this kind of stuff, but it's very far from the truth of what we're doing.
Matt, you're calling it boring, but I can't think anything too much more exciting than sending out autonomous robots basically into space to extract resources, bring it out back to the Earth so we can bring them back into the most complex supply chain we've ever created on this planet, which is semiconductors, not to mention all the other applications. Jim, another thing we were just kind of touching on is like, my understanding is, I'm just going to ask the space science question so you can give us a kind of a high level here. But so there's the large bodies like we live on here on Earth, and then there's small bodies. Right. What's the difference between these things? Why are they different? How come there's so much damn platinum in these things that are easier to get at?
Where the heck did this heavy metal stuff come from? You know,
we
all like rock bands, but that's not what we're talking about. So you know, when you think about the science, here's a little overview. 6 important things to know about small bodies in our solar system. And it really starts by an understanding of our collapsing cloud 4.6 billion years ago. It creates this pancake and little dust particles that are not only generated by other stars and blown into our nebula, begin to accrete and create larger and larger bodies. And so small bodies begin to be accreted, and they get big. If you accrete enough of them, you have a moon-sized object. If you accrete even more, you have an Earth-sized object. And in fact, when we look in the solar system and beyond, there are many planets out there that have been created. So what happens when a small body comes together? If it gets a certain size, it begins to melt. And that means all the heavy material, the little bits of iron and the little bits of platinum group metals that are created in stars and in clouds of supernova that are exploded and these metals are created, they begin to come together as they sink to the bottom. And in fact, that process is called differentiation. And when we're talking about mining platinum group metals here on Earth, we're really talking about mining things that have hit the Earth in the past. And these platinum group metals, these heavy atoms have been accreted in these cores, and then they hit the Earth and they're in the crust. And that's what we're mining out. And so we're only mining those things that were brought to us late in the evolutionary position of the Earth, after the Earth was created and it had its crust. Now you bring these objects, and now we're going to mine them. Well, we mine them in South Africa. We mine them in Asia. We mine them in China. But in anywhere from 50 to about 200 years, we will have mined out all the platinum group metals. Therefore, where can we get them? Well, we can dig it through our crust, dig through our mantle, and go into our core and get them. Well, that ain't going to happen. We can't even get to the mantle. Okay, we get down 2 miles, and and that's as far as we can get. And platinum group metals are so important because they're everywhere. You know, they conduct electricity and they don't rust. And that's one of the major reasons why we like to use them in all our computer parts. So indeed, it's going to be a handful of decades for which then the price of them is only going to skyrocket. It's only going to get more and more expensive. And yet they're all over the place in our solar system, in our small bodies.
Okay. That's really interesting, Jim. So it's just easier to get at them because of the way the solar system was formed, is sort of the net of
Well,
that.
yes, then go into our core. We ain't going to do that.
Right.
So we have to go out. Now,
okay, I have a million questions about how we can actually go about doing the extraction part from the solar system economically, which is why we asked Matt to come here. But Matt, can we kind of start with the big picture? Like, I'm just curious about your personal story. Like, what led you to this? Like, what's your background? How did you start thinking about this problem?
Sure. I think, for me, the real start of this company was when I was a little kid. I grew up very close to Pasadena, and we got tours of the Jet Propulsion Laboratory all the time. And that was always what I loved. And even though this wasn't really my generation, the Carl Sagan Cosmos theory, series, and really looking at Voyager and thinking how cool those spacecraft were and what they were able to do at that time. The honest truth is, for my generation, I think a lot of us lost interest in space because we built this boring thing called the space shuttle. And let's be honest about it. Like, it was a dream killer. We didn't care at all. Like, we'd already gone to the moon. Cool. And then we're like, let's go to low Earth orbit a whole bunch of times and kind of pretend it's reusable, even though it costs more than making a new one. Like, it really turned a lot of people off to space. And so, when we started having this new, let's be honest with it, Elon started a little bit of a revolution here when he said, like, why does ULA charge so much for rockets? I can do this a lot cheaper. Let's go try to do it cheaper.
Sure.
And he might have been a little wrong on some areas, but overall, he was pretty damn right. And he really kicked off something. And I joined one of those new space companies called Virgin Orbit very early and saw that process all the way through. Virgin Orbit, amazing engineering concept, right? Like, we get to drop a liquid-fueled rocket, 2-stage rocket off the wing of a 747.
Right.
That's pretty awesome.
Right.
I don't think the business case made any sense, but nobody really cared because the engineering part of that was so fun, right? Like, you could, like, could this even be done? We didn't know. And it turns out that a lot of the things we didn't expect really, I think, are what made that rocket have exceptional, really high costs that just made it not reasonable. So because of that, I actually left Virgin and went to a company called Bird Rides, which was a scooter company. And a lot of, my friends all made fun of me. They're like, hold on, you're going from being a rocket scientist to making scooters. And in short, the answer was absolutely, because I realized what was missing at Virgin, which was this whole sense of business. So I literally went to, at the time, which was the fastest growing company in the world. I really wanted to understand, how do you do manufacturing of hardware at really, really low cost? Like, if we don't look at this as a government project or what we go through, what can we do? And I learned so much at Bird, but I think two things really happened at Bird that made a big difference in my life. Number one is, one of the people I worked with and really admired at Virgin tried to recruit me to JPL very heavily to go work on the Europa Clipper mission. And he tried to recruit another guy at Bird too, called Jose, to go do this mission with us, right? And so he kept, and we, I met Jose at Bird. I went and talked with him, and I said, like, man, this is like what I've always wanted to do. I want to go dream. I want to go explore the solar system. But I don't know if I could sit there for, the mission duration at that time is listed at 32 years. I'm like, okay, cool. Maybe dead before this thing even gets there. Like, it does all its science, right? Outlives the mission. And I'm going to be this little tiny piece in this huge government machine that we're going to see go through. That's not really what I want to do. Like, I'm not ready to go, rudely say this, I'm not ready to go retire yet. And that's what I kind of view JPL as, like a great retirement gig. And Jose said, I think the same thing. And I said, well, can we look at this like Elon looked at Falcon 1? Like, let's just go do math on this. Europa Clipper costs $4.5 billion. Why?
Right.
I don't know how you make it cost that much. Like, you could literally build the thing out of gold and it would be cheaper. What am I missing, right? What is wrong? And we went through and we really did a whole bunch of just first order, like, how much does this cost to actually make if we did this, right? And when you go through it and you realize Europa Clipper is not that expensive.
That's right.
The jobs program associated with Europa Clipper is very expensive, and that's what we're seeing right at the end of the day. That's what gets you to that total 4.5 billion. But if we can make the assumption we can make these things a lot cheaper and have it be for an economical use case instead of the end goal of making money off a government contract, right? That's what universe exploration really is right now when people look at it from a business standpoint, is making margin on government. What could we do? And we came to this conclusion that we can actually make these things extremely cheap. And if we can make them extremely cheap, we can go take another stab at mining asteroids again. Companies have done this before, but if you can assume that spacecraft and entry costs to get to deep space are orders of magnitude lower than they've ever been, I think this can make a lot of economic sense to do again. Now, I also had a whole bunch of other stupid ideas that I'll neglect for this program that were just comical to even look back on, right? Like, anybody looking at what you can do when you kind of notice this opportunity, we had a whole bunch of ideas. But the one we settled on was, let's go take another stab at asteroid mining, but let's also do it for a market that exists on Earth today that's quantifiable. So you're making, so every investor we go talk to is really making an execution bet on us. Can we build a spacecraft for this price point? Not what happens if we do. I think everybody realizes if this company is successful and we pull it off, this is a massive industry. Like, we can truly disrupt all mining on Earth when it comes to the precious metals. And that's kind of the goal we're going after.
All right. So I'm really interested in understanding a lot of the huge technical challenges, though. I hear you when you say that everyone knows it can be accomplished. It's just execution at this point. But there's got to be a billion problems to solve in this. So I want to get to that. And kind of the structure of the way we kind of cover things on this this show is sort of there's a bits and then there's an atoms aspect to it, and Jim is completely on the atoms, I think, and my focus is bits and the stuff that exists in software. I think there must be some pretty amazing software behind this technology as well. But Jim, what I mean, we just talked about a whole bunch of missions up through and including the Europa Clipper. Like, why are these things so damn expensive?
That's important to know, is that when we go out into the solar system, we have a destination, and that destination is all over the place, and it's at various distances from the sun. And so consequently, that means to power the spacecraft, you've got to be able to analyze how much power you need, how much power you will be able to acquire from the sun. Is that enough? Can you build big enough solar arrays? And if not, now you've got to go nuclear. And now, just to start the process of bringing in a nuclear power source is at least $150 million. So these engineering decisions are done early on to try to figure out what the cheapest way is to construct and build the mission. We've studied Europa, going to Europa for probably more than a decade and a half before we actually settled down on what Europa Clipper can do. So when I was head of planetary, even starting in 2006, I kicked off several studies, and each one of them weren't cutting it. They just didn't have it. And the problems with it really boiled down to the environment Europa is in. Europa is in the middle of the radiation belts of Jupiter, okay? And so it is getting hammered by high energy particles. And so now we have to have special components that can survive the radiation. So instead of going to Radio Shack, if there is such a thing anymore, and buying your resistors, you can't do that. None of the conventional components you can buy. So now you have to buy specialized components. So now you've got power problems, and then you've got component problems, and then you've got, you've got to radio that data back. And if you're orbiting Europa, how long can you last? And it turns out the longest time you can last at Europa, orbiting Europa, is 90 days. Now, during the time period that I was head of planetary, we had a mission called Phoenix. Phoenix landed on Mars, and it was designed, and I mean, like in the Arctic area, the polar cap was eventually going to take over Phoenix. It was going to be covered with snow in like 3-4 months as winter was going to overtake it. Okay. So we landed it in the polar cap before the snow came, and we dug into the dirt, and we were looking for how deep can you go before you find the water layer, and it turns out it's almost at the subsurface level. The frozen water is right there. And so, but 90 days, the teams trying to do their experiments had to stay up day and night. They would get little bits of sleep. They were working on Saturdays and Sundays. They were just literally exhausted in a matter of a handful of weeks. And I don't know about you, but when I get exhausted like that, I then begin to make the wrong decisions. I then begin to do things that don't make sense. I then begin a process for which I'm trying to cope, and I can't. And it's because I'm not fresh. And so the 90-day mission on Phoenix did a fantastic job, but I could see how exhausted the team was. And then I turned to the JPL people constructing our Europa Clipper, and I said, look, we got to do something different. We want to be able to get a global map of Europa. Yes. And how we've been doing it in the past is orbiting it. But how can we get a global map without orbiting it? Well, one of the JPLers, in fact, this comes from the Cassini group at JPL. They said, well, we're getting a global map of Titan only because we do all these flybys. And if we manage the flybys just right, we can get 85% of the surface coverage of Titan in radar images of the whole surface in that manner by these multiple flybys. That was genius. And that enabled us then to do another thing. What Europa Clipper was going to do with a high resolution radar is the radar was going to penetrate the ice and get reflections back, analyze that, and then what was to happen is you got to radio the data back. But we couldn't radio all the data back. So we had to have onboard intelligence, okay, to scan the data, to subset it, to do whatever, all kinds of different analysis, and send part of the data back. And when we get part of the data, then we were going to make decisions on only part of the data. That is doomed for disaster. But once we started orbiting Jupiter, we could do a high resolution radar scan as we pass by Europa, go out around Jupiter and send all the data back. Then we have everything that we need to analyze it. So that was the key. Once we got to the point where we created a mission architecture that would work, then Europa Clipper, instead of lasting 90 days, will last 2 years. And so that's a real game changer. But it's not cheap to do.
Interesting. So there's a problem with bandwidth, basically, of transmitting the information back to the Earth.
Well, it's
so
one problem after
sampling methods.
Yeah, it's a problem with the electronics. It's a problem with the power. It's a problem with the bandwidth. It's just one thing after another, and to throw more and more money at it, trying to solve each of those, and then have such a short duration mission for which we may not be able to meet our objectives. Well, what's our objectives? Well, our objectives are to understand that ice crust, to see what's there. Is there carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, all the right materials that is used is not only creating life, but food for life. And so really the habitability of the moon is the critical thing. And if we can't get the data to determine where life might exist inside Europa, and how we might get there. I insisted that we have a high resolution imager on Europa. You need a high resolution imager. I mean, you're in your living room, and I'm in the kitchen here. Matt, you're at your desk. You look around and you see that little table that's sitting in your office or in your living room. If that's sat on Europa, I want to be able to image it. I want to be able to see it. Okay, and the reason why is you need that high resolution imaging to land. We need to land.
Let's maybe pivot to that and talk about sort of, because we're at opposite extremes here. Like these space science missions are still like multi-billion-dollar missions.
Yep.
I don't think Matt's mission is going to be billions of dollars. In fact, my understanding is like the target is to actually see if we can create an economically viable return orders of magnitude less than that. So Matt, I'm curious to have you talk a little bit about the technical challenges and how also you think about the economics of that, because what you originally said was it's about a business case. And by the way, we've got a bunch of people kind of tuning in here and watching live. If you have questions, we'd love you to ask questions. It doesn't have to be just me and Jim asking Matt questions here. Ask questions of the whole panel. Go ahead, Matt.
For us, it's a very different mission. I want to draw a big delineation here, I guess, Jim. When you guys, JPL or when NASA has sent out some of these interplanetary missions, whether it be Psyche or Europa Clipper, which launch will be coming up, we're pretty damn sure those things are going to be successful. In most cases, we're very sure they're going to be successful. And most of the engineers will have this, when they're watching the launch, they can enjoy the launch because they know all that hard work they've put in will lead to this success. The philosophy of my company is completely 180 different. I tell every engineer here, if you're not scared when we launch, we went too slow. And that's my honest thinking here. Like, I don't go into this with any kind of NASA Class A missions have 99.49s of reliability when they come to them. That is not us. And I think that is as simple as you can be to say, where's that cliff to make this a lot cheaper as we go into these environments.
Right. At NASA, the phrase we use is, what keeps you up at night?
In the software business, by the way, like, it's funny to compare this to software, because if we launch a live service, it's like, oh, it worked? Amazing.
And we're kind of
People
somewhere
are
in the
using
middle,
it and it didn't just implode.
right? We're going to be somewhere in the middle between, what keeps us up at night here is everything. I mean, let's be honest about it. But we also simplify our mission dramatically. So number one, we want to go after near-Earth asteroids. I'm not going to the belt. I'm not going to Jupiter, which the radiation problem on Jupiter, we can look at the Juno mission is a totally other beast that I'm not trying to take on at all. We have plenty of cases that we know about, where we say the spacecraft will fail. We build a spacecraft that has one point of failure on it that it can withstand at any point, and that's it. So we're not triple redundant. We do expect to lose spacecraft, and we expect this to be something that we do in a rapid iteration fashion as we go out. And because that's the only way to get the price lower. Like, I cannot get the reliability out of Europa Clipper and pretend the price is going to be lower because I'm commercial. To some extent, I mean, to be honest with you, maybe we could get an order of magnitude cost out of Europa Clipper. Let's say we could do that just because we're commercial and we want to go faster, blah, blah, blah. That's still $450 million. I don't have $450 million, so that's not going to happen. We've been pretty open about this as well, saying that our mission 2 that is coming up, which will launch in November, it's going to be aboard Intuitive Machines, launch 2. So it'll be on a translunar injection orbit that we will leave from, and we will go out to an asteroid. The total all-in cost for that mission is less than $7 million. Wow. That is where we are at, and that is what we are trying to do. And that is, I mean, you can assign whatever risk posture you want to that. I'm going to assign it really, really high, right? But that's how we look at this, and that's the only way you kind of change the world on this and make a big impression and make a big splash. I think if we're successful on this mission, I hope it gives the world a different way to look at space exploration, and maybe more of the software way, in a way of this rapid iteration, this quick prototyping, this higher risk-taking way to look at space exploration. But the chances are we're going to fail that mission. And I want to set expectations correctly on that. But this is a high-risk, high-reward mission that has a very, very small chance of being successful. And we're still all here every single day, every hour of every day. Jim, I think we're past the 90 days all in. Like, I don't even know what day it is. Like, everybody here is extremely tired. And we're still willing to put every effort we have and all of our life into trying to make this mission successful. And I think that's the big difference.
This reminds me of early NASA. Early NASA is, we hadn't any missions, and we were trying to figure out what things are like between the Earth and the Moon. So we launched several missions to just orbit the Earth and see what the space environment is. And that's where the Van Allen radiation belts were found. And that's where the magnetosphere was found. And that's where the solar wind was found. All that stuff, we were surprised by most of that. Some of that we had ideas, but we really didn't know what was happening. And then we wanted to see what when the sun gets angry, how bad is that? And does that affect humans if they're in a spacecraft? And let alone going to the moon. So some of the planetary scientists thought, well, if you land on the moon, there's so much regolith, you'll go in up to your chest. Okay, you just step off and bam, you just go in. Planetary scientists thought that. And so we kept launching. The first 4 missions to the moon that NASA launched all failed. Okay, and so the difference today is we have an enormous amount of basic knowledge about going into space to build on, to then say the things that were so risky for NASA in the early part was everything. And now it's still risky. Going into space is always risky, but you can buy down some of that risk by leveraging technologies we already have developed and know about. So it's a perfect time for many companies to stretch their legs and start this process of going out.
So we're starting to get some questions from the audience here. Just one quick thought, though. I mean, I think that's a really interesting observation, which is how can space technology start to follow more from sort of the failure is kind of acceptable through the process of iteration and learning that we have in software. I mean, 7 million is high for software, but relatively low for space technology. But one interesting comp is like training AI models. Like right now, there are lots of people training AI models where it's costing 7 million or 70 million. And we're even talking about, multi-billion-dollar training runs for some of the AI models that are being looked at now. So those are sort of the software equivalent of moonshots. And people have a reasonably good idea of like why it's worth spending that kind of money on AI. But this is something that could be really game-changing for the entire supply chain of the Earth. We had a couple of questions come in. I'll start with the first from Alder here, which is what areas of tech where investment is needed to perfect off-world prospecting. So Alder, maybe Matt, can you comment a little bit on like what are those areas of technology that we need to refine?
So, I mean, one of the biggest challenges we have as a company is that we want to go after a very specific type of asteroid, right? There's, like talk about this interplanetary core, which we refer to as metallic asteroids. That's what we want to go after. We don't care about a Bennu or any of these, like a carbonaceous asteroid does nothing for us. We have to find a metallic asteroid. So there's the really brute force area of tech investment here, which is just build bigger telescopes and spend more time taking pictures of asteroids so we can make correlations to M types or not. But, I don't know if that's really going to make a difference. I think for us, what I would love to see, or what I wish we would do a mission to that I'm kind of bummed out that they keep getting canceled that we haven't, is we just haven't done a lot of asteroid flybys. And I think there is, I've done a lot of trajectory analysis here. The team has looked at it. On a very low delta V craft, you can fly by quite a few near-Earth asteroids in one mission. And it's surprising to me that NASA hasn't gone after one of these as a lower class mission to go after. I mean, we are going to have, Hayabusa is going to fly by 1988 KY-26 in 2032. That'll be awesome. That'll give us some data to update our models. We obviously will have the Apophis asteroid flyby, which OREX or whatever they renamed it to now, flyby 4 days before. Yep. It's a bummer we're not going to get after to see if that thing is solid or not, right, as we go forward.
Well, we'll learn a little bit about how massive it is through the flyby, because the gravity will affect its trajectory. We'll learn something.
We're definitely going to learn a lot.
Is the hesitancy on asteroid missions in general, was that asteroids aren't sexy enough? Is it a budget issue? Is it a planets are cooler? Like what's the reason?
Okay, so Matt has a good point that we want to go to a bunch of asteroids. One of the reasons why we want to go to a bunch of asteroids is when we look at them, and there's millions out in the asteroid belt for which we've cataloged about 300,000 or 400,000. And there's at least 60,000 of them that are crossing our orbit and in and around our area that we call near-Earth objects, which come out of the asteroid belt. Jupiter throws them out, and it either throws them out of the solar system or throws them inward. And when they come inward, they're near-Earth objects. They can impact the Earth. So they're hazards on one end and resources on another because of what they contain. But in reality, when we look at them from Earth and get their light and then get a spectrum, the spectrum seems to be washed out. It's hard to tell what's going on. And the reason why is the upper part, the crusty area of an asteroid, if you will, is hammered by the solar wind. They all spin and they're bathed in the wind from the sun. And that wind overall then destroys some of the features of a spectrum that would tell us, wow, that's one that's more important than this one because it's got this and not that. And so we have classified then these asteroids by their spectra, and therefore those classes, if we go to one and dig in the dirt or bring back samples, we then can understand the spectrum in more details and then classify a whole bunch of them all at once, because we then can match all these have to be, maybe even a parent body from what we're talking about. If you build up a really big asteroid and all that stuff melts to the center and then other things hit it and you blow away the crust, now you've got the metal part. Now you've got the core part of a bigger body that Matt wants to go after and go get. So we've actually gone to maybe 15 or so asteroids. And there's been flybys. On our way to Saturn, we flew by a couple asteroids with Cassini. So we try to opportunistically go to several. One mission like Dawn went to the two biggest asteroids in the asteroid belt, Vesta, which is 500 kilometers in size. It's differentiated. It has a core, has a metal core, and then it orbited it for a year or two, and then the ion engine allowed it to increase its orbit, break its orbit, and then go after another asteroid in the opposite end of the asteroid belt called Ceres. And that's the biggest one. And that's 1,000 kilometers in size. You know, that Ceres is the one that is focused by the science fiction engage. I'm sorry. You know, the science fiction stuff that we were talking about earlier on. That's where Ceres has got plenty of water. It's actually wasn't created in the asteroid belt. Actually, it was probably created in the Kuiper belt. Like, it's more like a Pluto object and brought in over the changes that are occurring in the solar system.
Sure. And Ceres station, back to the Expanse, Ceres station was a major part of the Expanse,
right.
But sounds like we're going to get a lot more out of metallic asteroids before we're going to send, I don't know, 10,000 people to go live on Ceres and hit it with
we had the chance after orbiting Ceres with Dawn to go after other asteroids, to go after another. And the decision was, let's not do that. Let's stay in orbit and get down lower in altitude and get high resolution images because we want to land on Ceres. And so the decision was made at that time: do we go after other asteroids, or do we land? Do we feed forward, get the imaging, get everything we need for the next process, which is to land? You have to realize in planetary science, it's very methodical. It's flyby, orbit, land, rove, return samples. Now, we've done all that to the moon. We're in the process of doing all that for Mars, and we need to do that for more objects. And some of those objects, indeed, are our asteroids, and that's why returning samples. So Hayabusa 1 returned samples, told us all about how the solar wind was implanted in the surface. That's where we figured that out. Hayabusa 2 brought back samples from Ragu, a carbonaceous chondrite, not the kind of thing that Matt's interested in, but one of those things that has amino acids and has all kinds of good stuff in it, you know, that may have started life. And then Bennu from Bio-OSIRIS-REx. So we now have started to get those samples that we wanted to get to really understand how these small bodies relate to one another.
Okay, so Matt, can you take us through what the mission looks like for your kind of asteroids? Like, start us from the launch and like getting out there and what actually happens. What is this robot, or what do you call it?
For us, it's a pretty simple process that we want to go employ, right? And let me talk a little bit more about the mission 2 that's coming up, because I think that's the more important one that I should give you all the details on, right? It's pretty simple for us. We leave on a Falcon 9 that'll be bought by Intuitive Machines. Obviously, they will do their lunar landing on that rocket, right? So that'll be the second attempt that they do. We'll leave on that mission. It'll be a very different rocket launch. So when you watch a rocket launch that goes to low Earth orbit, if you're ever standing next to one, they almost look like they turn. And that's because they are turning, because they want to go into orbit. They don't want to go straight up, right? When you go on something like a translunar injection, this will be a rocket launch where we'll be a ride for about 4 hours. The Falcon will just pretty much burn the entire time because we're not going into an Earth-based orbit. We will get ejected from Falcon about 4 hours after the mission. We'll do some correction burns to essentially dictate the altitude above the moon, so we can get not really a gravity assist, like more of a clocking out to the correct asteroid on the trajectory we want. And then we'll be in deep space for about 5 months. So we'll be flying for about 5 months on our way to the asteroid. Then, look, a lot of the work NASA has done has really paved the way for this. And when you talk about the first step being a flyby, that's exactly what we're doing. So we're using a really high resolution camera. I think probably will be the highest resolution single sensor ever flown into space that we will go do a flyby on. And the algorithm we use to do the flyby is actually very similar to the Dawn mission. So that is what we are going to be using to do. And we'll get about 1.5 kilometers away from the asteroid and take some beautiful images of it if everything goes according to plan, and then stream them back to us over the next about year, because we want to test out the vehicle for a total lifespan of 2 years in space. So that's what our mission coming up looks like, and that's what we hope to achieve. You know, as we go out to that, like I said, those are the long stretch goals that we hope to go for. The real goal that I think we can all plan on doing here, and what we really highlight the team on, is let's get to deep space. No commercial company has ever made it to deep space as a mission. Elon launched his Tesla into deep space, which was kind of awesome, but it wasn't really a mission, right? It was like, here's my Tesla going up, we'll take some pictures, and now maybe it'll hit the sun or something. We're going
Well,
to be.
it's now a metal asteroid. I got news for you.
Maybe I should go mine it, right? But for us, we want to show that we can get out there, that we can communicate with the vehicle, that our trajectories are correct, that the way we've done the calculations. Keep in mind, there's a huge difference here between a traditional deep space launch and what we're doing, and this is the fact that we are rideshare. This is a much more. You talked about software, John, at the beginning. This is an exercise that has taken us really about 2 years to develop, and just how do we even do deep space rideshare? Because we do not get to choose the time we leave the Earth. That is chosen by somebody else. So essentially, over the entire launch window, whenever you watch a Voyager, or Cassini, or a Psyche launch, they always are instantaneous launch windows where they will launch at a very specific time. And a big part of that is because they calculate a very specific trajectory to make sure they're going to make it out there. How the hell do we do it when that's not the case, right? And so that's a big issue that we have, and that's a lot of compute power we've used to make that a reality.
Yeah,
it's an interesting comparison.
You really need to scour that catalog of objects, such that as your launch window changes, different objects appear in that. And that's what's fortunate about NASA's mapping of the asteroid belt. That's one of the big things that we've been doing, is finding more and more asteroids. In fact, I was lucky that the Planetary Science Group found an asteroid, named it after me. Okay, it's a little bitty thing out in the asteroid belt. If you decide to go there, let me know. I'd love to see what it looks like. But in any event, mining that catalog is going to be real important. And then, if there's things like Mars in the way to get a little gravity assist, as you point out, that's even better. But you've got a tough job, and we're all excited about seeing what happens. I'm the biggest moral support you got.
These missions are super risky. Mars for us is way too far away. Keep in mind the farthest that really any of our trajectories go. And so part of what you said is very observant, Jim, is that we actually have a multitude of asteroids that we target and that we go through our algorithms, and we try to understand density and size and probability of being metallic and all these kind of things that go into it. But because we have a launch window that extends multiple months, we have to have multiple targets that we can go to at different times.
Right.
So that's a big part of it. But the farthest we're really looking away, to give you guys an example here, is about 25 million miles. We don't look at anything past that because it just takes too long. And for me, time is a big issue here. We make sure all our missions are short in time duration.
Sure. Yeah, and that means they're near Earth objects, which is the great place to start. We estimate that there's 60,000 near Earth objects that are about 50 meters and bigger. Okay, and we've been cataloging those since 1998. And so when I came into becoming head of Planetary in 2006, we had maybe 5,000 or 6,000 of them found at that time. And so we started, really putting an effort into finding more and more of them. Right now, we've found maybe 32,000 out of the 60,000 that we need to find. So that's half of them. But the key is that fortunately they are quite a large number that we are tracking, and that catalog is going to be real important for you to be able to find which one you want to go to.
From an entrepreneurship or technology landscape perspective, I think this idea of the ride sharing is worth kind of double clicking on, because I see the comparisons to other parts of the technology industry there that have made so many more business models more economically viable. So if we look at semiconductors, for example, it used to be that if you wanted to be in the semiconductor manufacturing business, you had to build plants and manufacture your own chips, and then you were in the business. Today, that is not the way semiconductors are made, other than sort of very old generation chips that are not as hard to make. But if you're NVIDIA, the most valuable semiconductor company in the world now, they do no manufacturing. So they contract out to TSMC, which is a Taiwan company that does manufacturing. And they do it not only for NVIDIA, but basically everybody who's doing advanced chips, Apple, et cetera. You can even see it in things like Amazon. Like Amazon has millions of servers, as do their competitors like Microsoft with Azure. So it used to be if you wanted to throw up a website, you had to actually buy a computer and get it connected to the internet and actually make sure it doesn't go down. And you'd have to have all those costs associated with it. And now you just sign up for an Amazon account. It's basically automatic. You can throw whatever you want on there. If you don't want to do it anymore, you get rid of it. They take it back into their, legions, beyond legions, millions of servers that they've got there. So ride sharing seems like a really fundamental shift in the business model that allows your business to get off the ground, Matt.
What's really
literally and figuratively.
Yeah. What's facilitated that is the ability to have smaller size spacecraft with all the functions. You've got to have command and control. You've got to have power. You've got to have your instrument. You've got to have all these things jammed into a small footprint. And now you can do that. Okay. And that's been the game changer. And that's evolved over time. It's too bad that hadn't happened, soon after NASA started launching stuff into space. But it's here today. And the form that everyone likes to talk about are CubeSats. And now more and more applications are becoming obvious. I mean, right now, one of the tremendously successful businesses uses CubeSats to observe the Earth. Planet is the name of a company that a number of students of mine in the International Space University, I'm delighted to say, I help teach, are now having a very successful business. They have 200 CubeSats in space observing the Earth, and they sell the data. So these technology changes, that's form and hardware, but the next big revolution is the software.
Kind of, Jim, I'll disagree with you on this a little bit. Low Earth orbiting rideshare, totally agree. But low Earth orbiting rideshare seems to be done for a couple reasons that are a little bit maybe on a business case different. I don't think SpaceX makes any money. In fact, I would guess that they lose money on transporter missions. And this is what we talk about when we talk about these kind of rideshare missions as we go forward, right? It's been difficult. Also, when you deploy from a transporter mission, it doesn't even matter if you find your vehicle right away. Who cares? Like, guess what? If you don't find it for the first month, it's still orbiting the Earth. This happened to us on mission 1. And the nice thing is we knew it was going to keep coming by and we keep having shots on goal on it, right? Rideshare to deep space is a totally different beast. We have on the hour of orders to find the thing, locate it, get an updated position, make sure we're correct, assign the right trajectory. Like, this is a very tight tolerance that we have to go through. The biggest thing here is actually what I'll say is just the cost. That's it. The technology's always been around to make it this small. The technology's been around, I would say, since the 80s to build these size. We're going to be a 100-kilogram vehicle to build a vehicle in this class. The difference is I don't have to build it from scratch. Where, the people before me, Planetary Resources, which was a great company, we've learned a lot from. The biggest problem I think Planetary Resources had is they couldn't go down the street and buy components. The nice thing for me is I can literally go down the street and buy reaction wheels or buy cameras or buy this, because it's all been developed by other people because we've seen this huge commercial space economy come online. And so it's really just the cost for me to have a shot on goal here. I think that size has always kind of been available to do, but even look at the Janus missions, which were kicked off the Psyche launch. Those were still missions that are, I believe, 16U CubeSats. I believe they were 32 kilograms each. Don't quote me on those numbers. Those still cost $55 million. There's still a fundamental problem there when we look at the classical way of doing things. You just have to be able, John, kind of to your analogy of chips. I mean, keep in mind when Intel and AMD, AMD was the first real one to really buy allocation at TSMC. Everybody thought AMD was dead. Everybody thought this is the stupidest thing ever. This is never going to work. And what they didn't, I remember that time because I remember that time. And I think what people failed to notice there is that the iteration and the technology iteration was dictated on not putting too much capital into building up infrastructure for chips, but being able to iterate quickly. And AMD choose the quick iteration. And Intel's market cap, I believe, is down since that day overall. I think they went from like 200 billion to like 130 million, right? Or 130 billion. It's just, for us, it's all about quick iteration and speed. And that's really what we lean on.
All right, guys, that was such a fantastic discussion. I want to bring on a very special segment. Jim, you're going to be a bit surprised, but that's always how we do it. John, we've been talking about air topics, and Matt, you're going to be put in this particular section. So first of all, we're going to introduce you to some really tough questions from Dr. Jeff. So I'm going to put a disclaimer on very quickly. Dr. Jeff took permission from Dr. Jim Green to utilize the likeness of his voice, just in case it sounds similar. So what we've done here is we've got a version of Dr. Jeff
No
GPT.
Scarlett Johansson drama.
Yeah,
Yes.
he's got some questions for you, Matt.
Except I approve.
So what I'm going to do is play the first question and just tell me if you can hear it.
Can't hear it.
All right. Right. So I'm going to start this. So I'm going to credit 11 Labs, and then we're going to get an opinion from you, John, after Matt.
We can land on Europa, but we can't pipe audio into into
All right.
software.
Let's go.
So, Matt, I'm Dr. Jeff. It's great to do juicy stuff. AstroForge aims to mine asteroids, right? Is that just an excuse for you to play with the coolest space toys, or what?
I can't answer this question because I have fiduciary responsibility to my investors.
All right.
Of course, I never said this.
That was an excellent reproduction of Jim's voice, though.
It really worked very well. Yeah,
That's my evil twin. Yeah, Dr.
I like
Jeff
it.
is my
I like
evil
it.
twin.
Any question Dr. Jeff asks, it is completely disclaimed by us. We have no control of the type of stuff
No
he
control.
comes up with.
Mm-hmm. I'm sure. Jim, I heard you recording those questions right before this talk, but I'll pretend like it's that. No, I mean, one of the coolest things about a company like this at the scale, even at the scale we're at, right, is that, yeah, you in a way you do, like, there's little rocket engines here. There's little asteroids that we buy or that were even loaned out from museums to us. And there's lasers and all this really, really cool tech that we get to spend every day around. And I think that's really what keeps you motivated every day you walk in the building, is like there's something going on that's different. I mean, nothing to belittle a B2B SaaS company or anything like that. But when you walk into a place like Gusto, if you've ever looked at the Gusto offices, it's actually right across this hallway from Astronis. And you look at Astronis and you're like, that looks awesome. And then you look at Gusto and you're like, that's a really nice office. But like, it's an office. It looks like, it's got some plants and shit. It's just not as cool. Like, you don't dream. And I think as soon as you walk in the door at a company like this, your brain starts dreaming. And that's something we get to capture every day.
Yeah.
Yeah, and surely there is a 10-year-old watching this right now, hearing that and thinking, you know what? That's what I want to grow up and do to be able to play with this stuff and build this stuff and explore the universe. So that's what's going to motivate people ahead of, the economic opportunity is making it possible, because if there wasn't the economics behind it, all this stuff really wouldn't be happening. But it's the dream that we're inspiring people with to be able to.
I hope that even if this company ends up failing and we're not successful, that if nothing else, we push a little bit farther, we make it to deep space. And we inspire a generation to just think differently and kind of break out of the norm. I think a lot of us, if you go to JPL now, and again, it's not ever to talk bad about NASA, they do amazing things, but if you go there is a process for every single thing you want to do. If you want to make a wire, you have to test it in all these certain ways. And I want to really push people to just ask why. And that's what we do here. I mean, we look at things like, some of these specs on how you test and just challenge everything single way. Like, what are we going to learn from this? Why was this implemented? Is this still valid? In a lot of cases, we're probably wrong, but we still push the other direction, and time will tell. But I think that's hopefully what I can inspire in the next generation.
Matt, you have your finger on a number of things. We have grown up in the business recognizing you want to test as you fly, okay? And that means you spend a significant amount of money doing the testing. When we were going to land Curiosity on the surface of Mars, and we missed our first launch window because our actuators, those things that move the wheels and turn the mast and all that stuff, was having trouble being able to survive in the really cold temperatures, which it had to, because that's the environment of Mars. So we missed our first launch window in 2009, had to go to 2011. That gave us the perfect opportunity to perform more tests. I spent another $495 million on tests. And it turns out that money was well spent, because that enabled us to get a 1-ton rover down on the ground. Now you can't test every piece right after the other until you actually fly it. So you break it up into little pieces and you test each of those. and the setup and the time, and those are all tough. But now we have the knowledge on how to do that. Now we could build a sky crane to print, just like we did for Perseverance. We kept all the design changes, and we went right out and we built had a company build the sky crane, the second sky crane for Perseverance, giving them the blueprints on how to do it. Didn't make one change. And so our business has grown up in this mode of continual testing. And some of the tests, granted, are probably not going to tell us what we need to know, are not worth doing, perhaps. We try to do the right stuff. But I think what we're going to learn, NASA is, from companies that are doing these things in a risky way, is how to do them perhaps better, in the sense of really fine-tuning the right things to test. Okay, we have a question.
We're talking about mining on Europa. I guess it's a question for you, Jim. I'm not sure what we would mine on Europa.
Well, Europa, what we would mine is the life. We want to go for life on Europa. Yeah, Europa, out of all the bodies in the solar system, in my mind, probably has the best chance of having life in it today. Okay. Now, with the cracks on Europa coming and going and material being spewed out, it's for sure that if there's life there, it's coming out in the cracks. Now, that may mean not complex life, but multi-celled life. What may be deeper in the ocean is more complex life. That's important to also try to figure out. So I think Europa is really an Europa Clipper is really an astrobiology mission, and it's our first. And at the end of that, we're going to know, hey, this is a place we need to go back, and we now know where to go because we got high resolution imaging to go right there. Put down a lander, and let the plumes from a crack that it's sitting next to slosh over the deck. Okay, with water coming out, falling on it, and it'll be ice because it's so cold. And then you take that ice and you melt it, and you move it into our microscopes and our DNA analyzer, and you take a look at it. And that's what a lander might look like. So what we'd be mining is an understanding of how this body is provided an environment that life is thrived. We'll see.
One final question for Matt. Matt, in terms of AI and artificial intelligence, I mean, you've seen generative AI and all these things, and even what we did with the voice. How do you see it being an accelerant when it comes to space? Do you think it's going to make things quicker, or do you think we need to still stay on the ground and see what potential it has?
I don't. That's the honest truth here. I think we've seen in aerospace as a whole, AI is a great a great keyword to use. But I guess if we're talking about AI and the way that it's being explored today with LLMs, it's not very useful to anybody in space. I mean, obviously there's some of the edge cases, like, yeah, maybe it helps you write a little bit of code a little bit quicker. Maybe it helps you search documents a little quicker. But I'm not going to be able to type into AI, like, build me an asteroid mining spacecraft and have it produce anything reasonable. I still think the big pushes that I'm looking for in AI, we've kind of used this word AI very haphazardly over the last 2 years as it's gotten more, we've had machine vision for a long time. And before that, we used to call it statistics. And like that branch of mathematics, is what we use in every single day of every single thing we use. But I think your question is more geared towards, like, how does ChatGPT help me? And the reality is, it doesn't really have a big spot in aerospace right now from that anybody's identified. I mean, Elon gave a talk on this at the Milken conference where he essentially said, we don't use it at SpaceX. There's not really a use case here that we can use it to really bolster our production or what we're doing. These are very physical industries. These are very scientific and math-based industries. And AI, I think, still has to make, in my opinion, a leap on the mathematical side to make a difference in what I would use it for. What AI is great for right now, and what I think we use it for now, is I'm terrible at spelling. So, like, it's great at correcting my spelling mistakes. But other than that, I don't really use it on a daily basis.
All right, some more feedback for the 10-year-old in the audience. Don't be too worried about ChatGPT taking your job if you want to be in space science, mechanical engineering, aerospace engineering, physics. You'll probably still be useful to civilization for quite some time.
I still think there will always be the needs for the fundamental engineers, and we've changed the name on what that means. But I mean, you can look back at computer engineering as a whole, or understanding transistors or understanding logic gates has always been kind of the fundamental root of what we build a lot of this stuff off of. Just go learn the basics. Don't worry about the latest hot tech trends. Don't worry about what you can do with that. Worry about the basics, get a good foundation, and then you can go take these leaps of faith and try to push somewhere in a different direction. And I think that's where you'll always see the classic engineer as a whole come to fruition.
Well, I think that goes to more my thesis for one of the big use cases of what these language models actually is, though, as you may not be using it to help you design something within the context of like any kind of complicated machine, but learning the things that you need to be able to do to actually accomplish that is a role for these. So language models are going to play a really increasingly important role just in education, like as a agent that helps you acquire information, find information. Yes, they hallucinate a lot still, and that will improve with time. But in terms of just synthesizing the body of knowledge that you have to gather so that you yourself can then become really useful in a lot of these applications, that's kind of where I see it. So maybe it's LLMs are a little bit more of a second derivative in this equation of how you get there than the problem-solving device itself.
Of course, I mean, I don't mean to. LLMs and just when we look at AI as a whole has been great for a ton of things. I mean, essentially, what is it used for today? And keep in mind, in the 1960s, like we would have to go look at a book on where to get an equation for how to do a trajectory, and then Google came around. I could Google how do you do a trajectory to the moon, and now I can type into an LLM and say, give me the equations to go do a transfer orbit, right? And like those things have just gotten faster. So the amount of time it takes for me to go get information from somewhere else comes faster. What I can't do though is say, make me a trajectory for a 100-kilogram spacecraft on this launch date to the moon. That doesn't work yet, and the math side of LLMs is still a little weak, and I think we've seen this across the board. That's pretty well known. And like I hope one day that I can just, I mean, look, from a CEO, from a capital allocation standpoint, if you can look at this at helping replace engineering time, like it just means you can hire less people and build faster. 100%, we're going to look at this all day long. The reality is there isn't a replacement for a thermal engineer right now in the LLM world. And until that happens, I'm going to tell you the honest truth, which is we're not going to make that. We're not going to make that leap yet.
Yeah, True. Makes sense. Awesome. Well, this has been a wonderful conversation. I've learned a ton. And I'm sure that everybody here listening in has as well. So this was great. This is the second episode. So we're just getting this series started. Matt, thanks so much for being here and taking part in this conversation and telling us about your startup and the vision that you've got.
Absolutely. Thanks for having me on, guys.
Our pleasure.
Guys, thanks so much for the show. We've approached the hour. So Matt, thank you so much for joining. Jim and alter ego Dr. Jeff, welcome. And John, thank you so much. Guys, we'll be having another episode coming up in the coming weeks. We'll keep you updated, but we hope you learned what the future can look like. And don't be afraid to fail. As Matt, you said, it doesn't matter how crazy the idea sounds, or it doesn't. The fact is, if no one does it, we're never going to get there. So with that, thank you all and catch you again.
Take care.